We have the pleasure to listen. Welcome everyone. We have the pleasure to listen to Alaa Boukholkhal from ENS de Lyon. He will talk about conformal embedding of Riemann surfaces in Lorentzian spaces.
Okay, thank you, Mike, and thanks to the organizers for the invitation. So today I am going to talk about this problem of conformal embeddings of Riemann surfaces in Lorentzian spaces and in pseudo-Riemannian spaces in general. Okay, so let's start first of all with what is a Riemann surface. So I recall that a Riemann surface is a connected smooth real surface equipped with holomorphic transition maps, and some examples include the Riemann sphere, that we can see it as the complex the projective space CP1, the complex plane, and the upper half plane, or any open set of C. And these three examples, why I call them fundamental examples, it is because they are the only simply connected Riemann surfaces. So the uniformization theorem tells us that the universal covering Riemann surface of any Riemann surface is biholomorphically equivalent to one of these examples. And since we are going to be interested in compact surfaces, so any Riemann surface will be a quotient of these. So either it will be Riemann sphere, or it will be an elliptic curve or a complex tori. Maybe complex tori, it is not used for one-dimensional tori, but I will use it here. And so it is either a quotient of C by a lattice, or it is a hyperbolic surface, which means it is the quotient of the upper half plane by some cocompact lattice in PSL2R. And the interesting thing here is that in all the cases we can equip this Riemann surface with metric of constant curvature. So for example, here for elliptic curves, we know that a lattice in C, so just translations, they preserve the flat metric. So we can induce a flat metric on any elliptic curve or any complex torus. And for hyperbolic surfaces, the magical thing that happens, that the biholomorphisms, the group of biholomorphisms of the upper half plane as a Riemann surface, is exactly the group of isometries that preserves the orientation on H2 for the hyperbolic metric. So we can equip any closed Riemann surface of higher genus by a hyperbolic metric. And so that's the idea. So from a complex structure, we have a Riemannian metric of constant curvature compatible with it. And we are going to see that the inverse is also true. So any Riemannian metric on an orientable surface will induce a unique complex structure. So it is not necessarily of constant curvature. Any Riemannian metric, orientable. This is the only condition that we need, since Riemann surfaces are orientable. So if we start with a Riemannian surface, orientable Riemannian surface, so we have in local coordinates, we have this general form of the metric, and we can even write it in complex coordinate as follows. So we have two functions, lambda and mu. So lambda is a positive function, and mu is a complex function of norm less than 1. Okay. So any Riemannian metric can be written in this form. And now, if we have a Riemannian metric and we can find a coordinate system or local chart where the metric is the Euclidean metric times some positive function. We call this coordinate chart or this coordinate system isothermal. Okay, and having isothermal coordinates will be interesting. Is the way that we are going to obtain a complex structure, since if you have isothermal coordinates, the transition map will preserve the metric. So they will preserve this form of the metric. So they will preserve angles, because this is just the Euclidean metric up to some factor. And if you preserve this metric, then you preserve Euclidean angles, not distances but angles. And we are going to see that this is sufficient to have in a holomorphic map. So if you have a C1 map that preserves angles between two domains in C, then it is holomorphic. This is just the Cauchy-Riemann equations. Okay, so the idea is from a general coordinate system, we want to get this isothermal coordinate system, and then if we can do this, then any Riemannian metric will define a system of complex charts. Okay, so we are going to search for W such that the metric has this form, and this is equivalent to saying that that W written in the Z coordinates, it verifies this formula. We just write the equality. This comes directly, and we get that the only condition is that W satisfies the Beltrami equation, which is the following equation. And it turns out that this equation has always a solution. Okay, this was known since Gauss. So Gauss proved it for analytic metrics, and then the results were improved for C infinite and even measurable. It gives a complex structure, and if we notice that the Beltrami equation, it depends only on the mu factor. So if we go back to our metric, the factor lambda, it does not play any role. And this means that if I multiply the metric by any positive function, I will get the same isothermal coordinates, and hence I will get the same complex structure. So the complex structure coming from a Riemannian metric, it depends only on the conformal class of the metric. So it depends on the metric up to some positive factor. And so, as I said, since we will get now the transition map between isothermal coordinate are angle and sense preserving diffeomorphisms, they will be holomorphic, and we get our complex atlas. Okay, so one example, if we take the torus of revolution, so take a circle in the YZ plane and rotate it around the Z axis in R3. So we will get a torus like this. It has a very nice parameterization, and this parameterization, if we see the induced metric, the Euclidean metric, it will have this form. So it is not isothermal. These coordinates phi theta are not isothermal. But if we use this change of coordinate, change phi by psi, we will get an isothermal coordinate. And the metric will be just the Euclidean metric times some positive function. And I need to say that finding isothermal coordinates explicitly is a very hard task, and it is not easy usually it is not very easy. I can give just one example. If you take this torus of revolution and you just take its image by some diagonal matrix, non-trivial one, not a homotopy, then the Beltrami equation becomes very complicated, and we cannot get explicit solution to the Beltrami equation. Okay, so what is the conformal embedding problem? So so now we know that from any complex structure or any Riemann surface structure, we have a Riemannian metric. In very nice, we can have a Riemannian metric associated to it, and vice versa. If we can have a Riemannian, if we have a Riemannian metric, then we can define a complex structure. So the idea would be that can we realize all Riemann surfaces by surfaces in R3, in the Euclidean space. So take a surface embedded in the Euclidean space and take the induced metric. So the induced metric will define a complex structure. And the question of Klein was that can we find all Riemann surfaces in this way? So in more precise terms, if we fix a closed orientable Riemannian surface, so we have a Riemannian metric, can we find a smooth embedding in the Euclidean space, into the Euclidean space, such that the induced metric is conformal to the metric that we fixed. Okay. So so here I am saying smooth embedding, okay? But if we allow the embedding to be just C1, then the question is, we can answer the question affirmatively by the Nash-Kuiper theorem. The Nash-Kuiper theorem, it says that for any metric on a closed orientable surface, this is just a special case, you can find a C1 isometric embedding into the Euclidean space. And this means that we did more than conformal, we can do isometric. So the conformal problem can be answered affirmatively. But if you go to higher regularity for C2, for example, we cannot find an isometric embedding of flat tori or closed hyperbolic surfaces. These are as I said, these are the nicest representative of each, like the metrics that represent each class. In each class, we have a metric, a hyperbolic metric or a flat metric. And these ones, we cannot find a C2 isometric embedding of these ones, basically because if you take any surface in R3 embedded, then the induced metric, it will have a point where the curvature is positive. And this is just because you can put your surface, you can find a sphere that contains the surface inside it, and that is tangent at some point. And this means that this point of tangency, at this point, the curvature will be positive. So the problem is not as simple. Okay. So the first answer was given by Teichmüller, who found the first examples of non-rectangular torus. So what I mean by non-rectangular torus, I mean a torus that is not biholomorphic to C mod some lattice generated by one and some imaginary number. Okay. So if this kind of if you take this lattice and you take the quotient of C by this, we call this a rectangular one. And I must say that the revolution ones, the tori of revolution, are all rectangular. Even if you take not a circle, if you take any curve, closed curve, and you take the torus of revolution that comes from this curve, it will always be rectangular. So it was not easy to find a non-rectangular example. So Teichmüller gave the first example, and then Garcia proved that every closed Riemann surface can be conformally embedded in the Euclidean space. He used some ideas of Nash and Teichmüller to do this. And then Ruedy extended this to open Riemann surfaces, so the non-compact case, and Co generalized the two results to the case where the ambient space is any Riemannian, orientable Riemannian manifold, not necessarily the Euclidean space. So we can, for any closed Riemann surface, we can find a conformal embedding in any orientable Riemannian manifold. Okay, so as I said, the ideas uses so much Teichmüller theory, so I need to talk about it a little bit. Yeah, but before that, since I will be talking about higher genus surfaces, not genus one, and obviously not the sphere, I will just say one thing about the genus one case. So these examples, the construction or the proof of Garcia and Ruedy and co, all of them are not constructive. So they don't give an explicit example of for each Riemann surface. And this is basically because, as I said, it is very hard to solve the Beltrami equation and to uh, uh, it comes back to this. But in the genus one case, so Pinkel found a recipe to find explicit embeddings for all elliptic curves, for all complex tori. Okay. So what is the recipe? So you take a closed curve in the sphere, S2, okay, and now you take its inverse image by in S3 by the Hopf vibration. So let me recall that. So S3 is we can see it as the unit ball in C2, and from C2 we have a projection map to CP1, the natural map, and CP1 is just it is S2. It's homeomorphic to S2. So you take a closed curve in CP1 in S2, and you take its inverse image by the projection, this projection, when we induce it on S3. So this projection is an S1 bundle. So if you take a closed curve and you take its inverse image in S3, it will be a torus. And it turns out that this torus will be flat with the induced metric of S3, the usual round metric. And if it is flat, then there is no Beltrami equation to solve, and we have the complex charts right away. So we can identify the complex structure. And he proved that we can get all complex tori like this. So now they live in S3, but if they live in S3, they conform. We can project them into R3 just using stereographic projection, because we know that S3 minus a point, we can the stereographic projection is a conformal map into R3, so it will not change the conformal structure of this tori. Okay. So I will include just some examples of some tori. And yeah, so this one, and you can see here, like when we want to find non-rectangular tori, we need to turn the torus a little bit, because we need to get rid of the symmetry. Okay, so now I will go back to the Teichmüller theory. So from now on, I will talk only about higher genus surfaces. Okay. So take a closed orientable surface of genus greater or equal than 2, and take the space of all Riemannian metrics, and we will take also the Riemannian metrics of curvature -1. So everything here is smooth. The metrics, we take smooth metrics, and we will take the connected component of the identity in the group of orientation preserving diffeomorphisms, and also the group of smooth positive functions. And we will see why we are taking all of this. So first of all, we said that we want to identify two metrics if they are conformal to each other. So we have the action of the the group of positive functions on the space of metrics. You just multiply the metric. So we want to take the quotient by this. But also we want to identify two complex structures or two conformal classes if there exists a diffeomorphism that takes one to the other. Okay, so naturally we would take the action by the diffeomorphism group on the quotient. So just take the pullback. But Teichmüller's idea was to take not the whole diffeomorphism group, but just the connected component of the identity. And why he did this? He proved that if you take the quotient by this group, then the quotient will be manifold, very nice manifold. But if you take the diffeomorphism group, you will find an orbifold, and it not so. So when we take the connected component, we don't lose so much, but we get a nice quotient. Okay, so the uniformization, I recall, it tells us that any metric is pointwise conformally equivalent to unique metric of curvature -1. So any metric. So this means that the quotient, the quotient by positive, just by scaling by positive functions, this, when we restrict the projection to metrics of curvature -1, this would be diffeomorphism. So here I am saying more than that. Like we have an infinite dimensional manifold structure on a minus and on the quotient. So saying I perhaps need to explain what is a diffeomorphism, but I mean the fact that it is diffeomorphism does not come from the uniformization directly, but it was proven by Fischer and Tromba that this is the case. So, and now we take the quotient of this by the diffeomorphisms isotopic to the identity. So basically, we are taking the quotient of the matrix of curvature -1 by the action, just the pullback action of the diffeomorphisms isotopic to the identity. And this space, we call it the Teichmüller space. Okay. So this space, as I said, turns out to be a very nice space. It will be diffeomorphic to the Euclidean space of dimension 6D minus 6. D is the genus of the surface. And we can put on it a metric or a distance, not a Riemannian metric, a distance called the Teichmüller distance. Okay. I will not explain what this distance is, but I will just say this fact that we will use afterwards. So we want to compare the distance between the complex structure defined by two Riemannian metrics. So if I have two Riemannian metrics, G1 and G2, I claim that the distance between their projections into the Teichmüller space is less than this quantity. And so this k, this constant k, basically what we are saying is that if we take the unit circle for the metric G1, and it will be if you take the identity map between the two Riemann surfaces, it will be a diffeomorphism, obviously not necessarily conformal. So it will send the unit circle for G1. It will be for the metric G2. It will be an ellipse, and this k is just the ratio between the maximal axis and the minimal axis. Okay, so we have a way to compare the distance.
Sorry, but
Yeah.
why it is therefore equal? It is equal to the Teichmüller distance.
No, not necessarily.
You are taking it in one point.
No, I take the supremum over all the points in the surface. Because here you are the Teichmüller distance. You are taking the dilatation of all quasi-conformal maps between the Riemann surface defined by G1 and G2. Okay, and it is not necessarily the identity. It is in most cases. It is surely not the identity.
Oh, okay.
We are seeing something else, a PDF or something like that. It's not the slides, yeah?
You are not seeing my slide?
No, I'm seeing like archive
oh, sorry.
PDF or something.
I don't know what happened.
Maybe you can like
someone else is sharing his screen.
Where is sharing his screen?
Okay, thank you, Ruedy.
Okay.
Moment.
Sorry for that.
Yeah.
Sorry.
No problem. Okay, so we usually we cannot compute this distance, but we can always find this. We have always this inequality, and this is what we are going to use. Okay, so so that's it for Teichmüller theory, and now I just want to reformulate the question, the conformal embedding problem, into isometric one. So what we are saying is that we are looking for a section from the Teichmüller space into the space of metrics. Section not necessarily continuous, just a section, such that any metric in the image admits an isometric embedding in the Euclidean space. Okay, so just another reformulation of Klein's question. Okay, so here we will be interested in the pseudo-Riemannian generalization of the problem. Okay. So I recall that a pseudo-Riemannian manifold is a manifold induced with along with a field of non-degenerate symmetric bilinear forms defined on the tangent spaces, of course with the same signature, and if the signature is n0, so we have no negative eigenvalue, the metric is Riemannian. If it is the signature is n-1, 1, then we call the metric Lorentzian. So perhaps this definition is for semi-Riemannian manifolds, and pseudo-Riemannian is when the Q is not 0, so we are not in the Riemannian case, but since I am interested in this, in the pseudo-Riemannian case, so when Q is not 0, I will call everything pseudo-Riemannian. Okay, so yeah, so one thing to add here is that so here in the pseudo-Riemannian case, since the metric is not necessarily positive definite, some vectors have positive norm, we call them spacelike. Some vectors have negative norm, we call them timelike, and some vectors have zero norm, we call them lightlike. And for an embedding of some manifold in a pseudo-Riemannian manifold, if the induced metric is always Riemannian, okay, we call the embedding space-like embedding. And what does this mean? This means that the tangent plane is always sent to a space-like plane. So a plane, in this case, for example, in the three-dimensional case, this green plane is space-like. It is outside the isotropic cone. Okay, so we need, and remember, we need the Riemannian metrics. We are working with the Riemannian metrics on our surface, so we need to find space-like embeddings. So now let's ask the same question. Let's take a pseudo-Riemannian manifold, okay, and take a closed orientable Riemannian surface. So can we find a smooth conformal embedding in this manifold M? So since we are talking about a conformal embedding, the induced metric is Riemannian, and necessarily the embedding must be space-like. Okay. So yes, so in other terms, can we find a section from Teichmüller to space of metrics such that any metric in the image admits an isometric embedding? And the answer is no in general, because we don't always have space-like embeddings. So I will give an example. So if we take the Minkowski space, so just the three-dimensional vector space with this Lorentzian metric, and so we can prove that any closed surface embedded in R3 in this Lorentzian manifold, it must have a point where the tangent plane is not space-like. Okay, you take any plane and it will be there is some point where the tangent plane is parallel to this plane. This is so in particular. There are some points where the tangent plane is not space-like. So we cannot find the space-like embedding inside any pseudo-Riemannian manifold in general. Okay, but so this is a necessary condition. We need to assume that at least we have one space-like embedding. We don't have this kind of topological problem. Okay. I think I will go just a little bit to define the objects, and then I will stop for this part. So let's take a context where this space-like this problem we don't have this problem. So take the timelike cone in the 2+1 Minkowski space. So I mean by this, so we have the light cone, the vectors of norm 0. Okay. Okay, it has two components. I will take just the upper one. So when z is positive, and we take the interior. Okay. So this is an open set in the Minkowski space. So we can take it with the induced Lorentzian metric. It is a Lorentzian manifold. We still have the same problem. We cannot find a space-like embedding of closed surfaces here. Yeah, and one thing about this space is that it will be isometric to H2 times R plus with this metric. So H is the hyperbolic metric on the H2 factor, and the R factor is denoted by small r. And this we can see it for example in this two-dimensional picture, is that when we take the cone, the levels of the Lorentzian form, so the negative levels, they foliate the timelike cone entirely, and of course the curvature will change since the metric is not exactly a product metric, but the levels will be all of negative curvature. Okay, so we have this space, and now in order we will take a quotient of this space. So let's take a cocompact lattice in the connected component of SO21. So the thing is that SO21 preserves the Lorentzian metric. So it is inside the group of isometries, and it preserves the cone also. It will preserve T. So it is in the isometry group of T, and since it preserves the Lorentzian metric in on the Minkowski space, then it preserves the levels. Okay, so then the group gamma, it will act on each level. It will not change exchange the levels or do anything, but it will act on each level. Okay. So let's take gamma to be a cocompact lattice, and if we take the quotient with this cocompact lattice, the quotient will have the form will be of the form S times R, because we said that gamma will act on each level. Okay. And of course, the level H2, the hyperbolic level, will give us a hyperbolic surface, a compact hyperbolic surface, okay, without boundary closed. Okay, so here in this case, the hyperbolic surface, we have a space-like embedding, but we have more than that. We have space-like embedding, but we have an isometric embedding of a hyperbolic metric on our on sigma. So sigma is just the topological surface. Okay, so surface with pi1 isomorphic to gamma. And one might ask, okay, so here I don't have the same abstraction that I had before in the Euclidean space. I can embed hyperbolic metrics. I can embed metrics of negative curvature. So one might say that, okay, for my problem, I don't have the topological problem of finding space-like embedding. So maybe let's go directly and prove that this we can embed all the hyperbolic surfaces, and this will imply that we can find the formal embedding for any Riemann surface. But it turns out that this is not the case. So the quotient is something like this. So it is the levels are surfaces, okay? But the as I said, the curvature of each level, it changes. There are two levels. There are no two levels that have the same curvature. Okay. So if you assume that you have a hyperbolic metric on sigma and you have an isometric embedding inside this quotient space t mod gamma, since it is compact, it will be tangent to two levels, to level SR1 and SR2, okay? And just so it will be tangent to two levels, and just by comparing the curvature at these tangency points, we can conclude that it must be equal to one of them. And if you assume that the metric is hyperbolic, then it must be the hyperbolic level, okay? So there is no isometric embedding of hyperbolic metrics except this trivial one, h gamma. Okay, so let's change the question a little bit and let's ask so we have a problem with hyperbolic, but we still can embed negatively curved metrics. Okay, so let's take the set of negatively curved metrics on sigma. And let's ask the same question. So can we find a section from the Teichmüller space into the negatively curved metrics on sigma, such that any metric in the image admits an isometric embedding? And so this space is huge, but it turns out that the answer is still no. We cannot do this. So I think I will stop here and explain more in the second part.